So we've talked a lot about constant pressure processes and constant volume processes, but I really want to convey that there are two different systems at play when volume is constant and pressure is constant. Under constant volume conditions, you have the change in the heat energy is equal to the change in the internal energy in the absence of non-expansion work. Okay, so this is in absence of non-expansion work. We'll get to more what that is in a second. Under constant pressure processes, think about it. What is this analogy over here? dQp is equal to what? You better darn well said delta H. So enthalpy, constant pressure. Internal energy, constant volume. Repeat after me. Constant volume, internal energy. Constant pressure, enthalpy. Constant pressure, enthalpy. Constant volume, internal energy. Again, constant volume, internal energy, constant pressure, enthalpy. I can't stress that enough. These are defined under these different conditions. So when we define these thermodynamic potentials, internal energy, constant volume, enthalpy, constant pressure, it's because that's a way that we can isolate a single process without turning both knobs simultaneously of both volume and both pressure. It does not mean there is no enthalpy under a constant volume process. It just means that it has that we've broken up the different process into just the constant volume and then just the constant pressure. Okay, so here we have, so for this one would be only expansion work. And if you think about what does H equal, U plus PV, that is pressure volume work, is expansion work. So if you have an additional work associated with the process and you've got, then it's going to be pressure volume work under constant pressure. Under a constant volume condition, it's non-expansion work if there is any work associated with the process. So U is equal to Q plus W. This is not going to come from expansion, because if it came from expansion, it would be U is equal to Q plus W PV work, and then this would be an entropic effect, or sorry, an enthalpic effect. Okay, so let's go back then. That was an aside. Here, I've got T delta S, whoops, sorry, T ds is greater than or equal to du. And then here I've got T ds is greater than or equal to dH. So this is for expansion work and this is for non-expansion work. For internal energy constant volume, A is equal to U minus TS. And again, this is the Helmholtz energy, where you can have delta A is equal to delta U minus T delta S for a constant temperature system, or a constant temperature process. I'm kind of reviewing all of this. Over here, you've got G is equal to H minus TS, giving us delta G is equal to delta H minus T delta S, again at constant temperature. Okay, this is the Gibbs energy, non-expansion work. What could that be that you might add? So this is only for expansion work. And then if you want to now look at, so there's expansion work. If you want to look at non-expansion work, you go here. Okay, Gibbs free energy has units of joules. Enthalpy has units of joules. TS has units of joules. And so what you're doing is you're isolating out the part, this is non-expansion work. Okay, this is expansion work. You're subtracting then off the entropic aspect. And so the difference between this and T delta S of the process is going to be the non-expansion work. What kind of non-expansion work could you have? I don't know if I have one here. I don't. Oh no. Think of a battery. Okay, so that's chemical energy. The Nernst equation, which relates the delta G to the potential difference of a battery, well, that's delta G. It's non-expansion work. We also call that chemical work. Go team. So to refresh, or not to refresh, but to reiterate, constant volume, think internal energy. Constant pressure, think enthalpy. Constant volume, internal energy, Helmholtz. Constant pressure, think enthalpy, Gibbs. Non-expansion work. Non-expansion work. Cool? Okay, now we're going to take a closer look at Gibbs. You can do the exact same thing that I'm about to do with Helmholtz, but we're going to play more with Gibbs than we will with Helmholtz. So what I'm about to do, you should be able to do after you see this. There are a couple homework problems that you're going to have to do this technique for, and it's really just exploring more of what the Gibbs has to offer. So let's break this down into what we know. G is equal to H minus TS. What is H? U plus PV minus TS. Okay, U, this is from the first law. We've got Q plus W, and I'm going to break this down into Q plus W pressure volume plus W non-pressure volume work. Okay, so now if I take this, plug it in there, I get G equals Q plus PV work plus non-PV work plus PV minus TS. Cool. So now what I'm going to do is I'm going to take this and I'm going to make this now DG. Okay, actually let me make that a little. So now I want to know, how is the change in Gibbs going to occur? Okay, well, this simply becomes dq. So now I'm in the inexact differential because this is not a state function. Plus, well, work is equal to minus pdv. Okay, and so then I'm going to say that, crap, this is not good. Stop.